All right, welcome back, everybody. You guys rested or stressed, or both? Stressed. Yeah. Did you guys know the next semester starts pretty late compared to normal? I just realized that yesterday. I think it's the 18th. January 18th is when we start. Usually like a week and a half before that. So you'll have a long winter break at least, right? Okay, so I want to pick back up where we left off. Just a couple notes first. I didn't get a chance to upload the last Tuesday's lecture to YouTube yet. It's still on Twitch if you want to see it there, and that's twitch.tv/snowslab, all one word. I'll be posting that to YouTube and then posting that to our Moodle page by the end of the week. And I'll do Thursday's exam review either Thursday night or maybe Friday. So you'll have that before the weekend for sure, posted on YouTube on our page, as well as it'll of course still be there. And I'll post the homework solutions and all of that. So you'll have basically all the content that I put out onto Moodle by Friday afternoon sometime at the latest. Homework is due on Thursday. I think I made a note in the instructions somewhere that I do like hard copies. I feel like I can grade them a little faster that way. I don't have to have them, so if you just want to turn them in the way you have before, that's fine. I certainly won't count that against anybody. I'm going to put a caveat here. I've traveled over the break myself, and my wife came back and has a cold. It's not COVID, it's not the flu. She just got checked this morning. I'm feeling great so far, and so I'm not worried. But the amount I have to talk Tuesdays and Thursdays, and incubation time, I might not be able to have a voice on Thursday. If I'm sick, I'm just going to live stream from home. I'll send an email letting you know that. If that's the case, then just upload your homework. Okay? So if you did want to turn it in person, great. If you do that, I do recommend you take a screen capture of some sort so you can have it as a reference. I'm not going to be able to get it back to you before the final exam. So if you do turn in a hard copy, make sure you do scan it if you want to study from that in class, if not later. Okay, hopefully I'll be here, happy, healthy, all that. All right, any questions about that? Okay, and I'll give my final comments on what I'm doing about the remaining grades on Thursday. I told you last time I'm thinking about giving credit for a certain amount of participation scores, just as if everybody got perfect scores, simplifying some things for both you and myself. So I'll give you the final word on that on Thursday, my decision there. Okay, so we'll get into the BOD. So here's where we left off last time. We were kind of in a hurry. I was trying to get through enough material to give you a chance, if you wanted to work on the homework over the break, that you could. So you might remember we were talking about BOD tests. You talked about that before, so that was good. I showed you this example problem. You gave you the chance to work that on your own if you wanted to, but I just had the text up there from a previous occasion. We'll go through an example or two today. It'll probably help cover that as well. So then we talked about what happens if you need to dilute a BOD test quite a lot, and you're going to have to dilute it so much that you have to add bacteria so that there's something biological that can actually grow. That's when we had the two bottle system where we have the mixture of both your dilution and the wastewater that you're interested in, and you have just the dilution water itself so that you can determine exactly how much BOD is in your end result. So essentially you have both the BOD of the mixture being measured and the BOD of the dilution water being measured with an experiment, and you're combining those two together to calculate the BOD of the wastewater. So that was the scheme, and if you simplify this in terms of the other components, and you simplify it so that you're dealing with just the dilution factor instead of these the P wastewater, or the volume wastewater, volume dilution. You can put it all in terms of P, and then you get this equation down here. Okay, so it's just a bit of algebra, and you get that. I'm going to post the equation sheet I would normally give for final exams. It will include this equation on it, so that may be a handy way for you to create your own equation sheet. Okay, so in essence, what we would do experimentally is we'd have some mixture. So this is our wastewater plus our dilution. We'll take that measurement in that sample, and then we're also going to have a bottle of just dilution water only. And that's going to give us our BOD for the for two different systems, and we'll combine that to get our final. I'm going to, if we take a look at that equation here, we have this in terms of the BOD of the mixture and BOD of the dilution. Well, in this next equation, I have it in terms of DO initial minus DO final. It's kind of the way we do BOD, right? I also have B initial and B final here. That's just the way my book that I use writes it. So B is simply the dissolved oxygen, the DO, in the dilution vessel. So DOI is the dissolved oxygen initial. BI is the dissolved oxygen initial in the dilution case. So it would be BI and BF here, and DOI and DOF. Okay, so that's just kind of clarifying what we're talking about there in terms of that equation. Okay, so I'm going to give you a chance to put this to use. This is going to be very similar to the BOD stuff you covered in the past, plus this little extra bit using this new equation here. So we have a test bottle containing just seeded water, has its DO level drop by 1 milligram per liter in a 5-day test. A 300 milliliter bottle filled with 15 milliliters, so this is separately. So a separate 300 milliliter bottle filled with 15 milliliters of wastewater, and the rest is seeded dilution water. And you could express this as a dilution of 1 to 20. So 15 and 300 is the same as 1 and 20. Experiences a drop of 7.2 milligrams per liter in the same period. So what would be the 5-day BOD of the wastewater be? So take a couple minutes and see if you can solve this on your own, and I'll work through it with you for you in a minute. Okay, so hopefully you had a chance to kind of take a look, think about what the problem is saying and how that relates to our equation here. So the BOD, the DO drop, it mentions this dissolved oxygen drop. Well, that doesn't give you an exact initial or final, but you don't need that if you know how much it dropped. So if you're given that drop in DO, it could have started at 10 milligrams per liter or 15 milligrams per liter. The drop is the same as long as you were able to measure it in a measurable range. So in that case, we can, instead of using this DO initial, DO final, we can simply put that drop. So here I put 7.2 milligrams per liter for the mixture case, and then 1 milligram per liter for the dilution water case. Multiply that by 1 minus P, and divide the whole thing by P. Now, if you take 15 divided by 300, or 1, that's equal to 1 divided by 20, which is 0.05. So 1 minus 0.05 is 0.95, and so this is what it will end up being if you were to write all that out. And so then if you solve, that's 125 milligrams per liter of BOD. Okay. Does that make sense? The issues? Okay. All right. So that's kind of the all I wanted to say about the BOD measurements themselves. Only slightly more complicated than what you'd already done, I think, if you hadn't seen the dilution water. Next, I'd like to get to modeling BOD downstream, specifically so we can understand something about when does the oxygen reach the lowest point, how far downstream is that going to be, how much time after the waste is discharged, which is related to the distance if you've got a stream flowing pretty constantly. So that's kind of an important analysis for any time you're discharging wastewater to a natural body of water, because you want to know where to measure to see if there's any bad impacts, or you want to know at what point would you expect the bad impacts or the worst impacts for dissolved oxygen deficits. Okay, so there's a few parameters involved, right? We've got the amount of food that's going through, and that's being eaten by the bacteria and stuff, and that's decreasing over time. You've got the amount of dissolved oxygen in the water, and that's being depleted by the biological activity, but also added back in just by nature of the water in contact with air, right? So we've got oxygen being put in, oxygen being taken away, and how do we know how that's varying over time? Well, that gets us to kind of these mass balance type models of what's going on. So I know you guys didn't specifically cover mass balances, but I'm going to give you the rundown on the simplest case, which is a batch reactor. Okay, a bottle of water, a jar, something there's no flow going in or out. It's just some water here, right? And then that means if we've got some accumulation of oxygen or maybe some depletion of oxygen, it's all in that closed system, right? So let's describe that as a batch reactor. We have some vessel, we're going to assume it's completely mixed, and there's no flow going in or out, okay? That's our batch reactor. If we want to take a look at the accumulation of something in it, we'll take a look in the volume. We have some change in concentration over time. That's going to be our accumulation. That's going to be like a bank account. You've got, you've got the account, you've got, if you have no income or expenditures, the only thing that happens in there is whatever interest rate, okay? So we're going to take a bank account with no inputs or outputs, just interest as a reaction. So that's going to be equal to essentially the reaction term. We can be a little more specific with that and write the reaction term as we could do a negative, some rate constant, let's say decay, times C, and maybe a growth, K growth times C. Something like that. And that would also be in a volume. So we'll say whatever reactions are occurring in that volume. So the simplest case of this batch reaction, let's just say we have 0 growth for a moment. The volumes cancel. And so a simple term of a first order decay here, don't worry about the first order, that doesn't make sense, I'm not too worried, is minus KC. So it's a constant and that. And to get this in a usable form, we need to integrate. And if you remember from your calculus or differential equations, this actually becomes a simple form where it's dc, and we'll get the c on both sides, and we'll get the time on the other side. It's negative k times t dt, k times dt. And then we integrate both sides. Now the integral of 1 over x dx is the natural log of x. That's the little trick you'd have to remember if you wanted to do this from scratch. We're going to do this from the initial c to the final c, and from time 0 to time. That's going to give us an equation that will be familiar to you, or it will soon be familiar. That's going to be natural log of c minus natural log of c naught. Rewrite that. Equals negative k d times time. Well, that's the same as our interest rate equation, essentially, if we've got a negative rate. So this is we can simplify with the natural logs. That would become natural log, this is just one of the algebra tricks, of c over c naught, is equal to minus k times time. Or we could take that and raise both sides, take e to the power of both sides to get rid of the natural log. So that becomes c over c naught equals e to the minus k dt. So that's a form you've seen a million times before. We just derived it from this mass balance of a batch reactor, okay, with some specific type of reaction. Just wanted to put that aside here to show you how the math flows from the idea of a mass balance. What's happening, there's nothing coming in, nothing going out, just some sort of reaction happening inside. We can do that with fancier reactors with flow going through them, all that, but it's essentially the same process. We want to know if there's accumulation and to describe the system accordingly. Okay, I say that because when we talk about a plug flow reactor is essentially a batch reactor on a conveyor belt. It's like you assume that whatever you have happening up here at the start of the river is not mixing with the stuff at the end of the river, right? There's no mixing from the start of the Mississippi to the end of the Mississippi. It's mixed probably within a little small area, and in this plug flow reactor system, we basically assume it's perfectly mixed in a very, very, very small slice. And then that slice is just moving through like a batch reactor on a conveyor belt, okay? So this is essentially a plug flow reactor. So this is analogous to a plug flow reactor, except instead of just letting it sit on my desk for an hour, we're going to put it on a conveyor belt and see how far it goes in that 1 hour, right? That's just the difference, right? We have that water flowing through, and then you can have continuous flow, but we're treating it like a batch reactor, so whatever reaction is happening in here is happening to all of the water that's flowing through. So that's the quick version of mass balances for batch and plug flow reactors. Okay, I wanted to say all that because that's essentially what's happening to our oxygen while we are depleting it, and the BOD, okay? So for the oxygen case, our biodegradation of stuff is depleting oxygen. That's a decay reaction dependent on how much food is in the water for the bacteria. And then on the flip side, the oxygen deficit is causing rearation because air likes to be in equilibrium with water in terms of the amount of oxygen. There's We have, what, 22% of our air we breathe is oxygen. Well, a smaller portion of that goes into water, but it's a defined portion. That's an equilibrium reaction. So if you take all the oxygen away from water, the air will push oxygen into the water. So that's happening at the same time. Okay, and we're gonna take a look at the math that tells us how to deal with that type of a system. So if we take a look at the dissolved oxygen in a stream or river, first we can identify that we probably have some saturation value. So this would be that kind of the maximum dissolved oxygen, I'll call it DO saturation. So that would be something like 8 to 10 milligrams per liter of oxygen. We're not going to go above that because the water can only hold that much. And in a natural body of water, we typically actually have a small deficit. So there's a small amount missing most of the time. So we'd probably start somewhere around here. And then as the river flows, we're assuming we have a discharge of wastewater at this time zero or distance zero. So we have a wastewater entering. Then what's going to happen is the dissolved oxygen is going to be decreasing given the oxygen demand, and then eventually it'll come back up near to the saturation. The way I drew it, it looks like it hits saturation. Typically, it's not going to quite hit there. So that's going to happen because our water, the stuff in the water is demanding oxygen, and at the same time, the air is restoring oxygen. But there's going to be some amount of time where we'll eventually hit a minimum, and that's going to be our critical point. We could call that the time critical, or if we're doing distance as x, that critical point there. So that would correspond to some distance downstream. Okay, yeah.
Does it look like the saturation or like the original level? Does when it levels up from like the right side, does it contribute to the saturation? Does it go to the saturation, or like only the original level it was at?
Okay, yeah, that's a good question. I didn't draw it particularly well. Does it get all the way to saturation? If there was really no sources of oxygen demand at the end of all this, it could. But that's not really realistic. And most bodies of water have some natural organic matter in it. There's going to be some oxygen demand. So if I were to draw it a little more carefully, try it again. It would probably look something more like that. So it'd reach somewhere up there. It just depends on the dynamics of the body of water. Okay. So another tool we can use a term called total organic carbon. This is just another metric of how much biodegradable stuff is in the water. I'm only introducing it because it's common to use for this type of a setting. You often will measure TOC in a body of water. It's really a lot like the COD measurement, the carbonation, the chemical oxygen demand measurement. It's just specifically targeting how much carbon is in there and discovering that. So it's related. You can kind of treat it as a decent measurement of BOD or substrate. So it's a useful tool, and what we can say is if we have a lot of TOC in our wastewater, because there's a lot of organic matter in it, then as we discharge it and as bacteria start to eat it, we'll see that decreasing over time. And again, most rivers will have some naturally in it from the sediment, from the soils running off into it, from fish and wildlife excreting waste and all that. So, but we can watch that decrease over time, and then if we consider overlaying that with the BOD, so let's say we have on the right here, we'll say the TOC axis, It's going to be milligrams of carbon per liter. So we'd have our TOC decreasing over time. And the speed at which that's happening is going to be related to the amount of dissolved oxygen that's in solution. Dissolved oxygen is doing something like that. And the reason that the dissolved oxygen is going back up is because it's no longer being depleted so fast, right? The less TOC we have, the more, the less food, the less TOC we have, the less oxygen demand we have. Okay, so it's a dynamic system where there's essentially the deoxygenation occurring from BOD, from biodegradation, and then the reaeration occurring from oxygen coming back in. All right. So, yeah. Okay. Does that make sense? Any questions? All right, so then how quickly is the BOD removed? So that's one part of the puzzle that we need to know. We talked about measuring BOD. I think you guys had already covered that. Did you talk at all about the BOD remaining term? Okay, so let's define this new term, L. So LT is the BOD remaining at time t. L initial, L naught, is the BOD remaining at time 0, or the ultimate BOD you could ever possibly have. So this gets a little confusing at times because we often describe BOD 5 specifically. Here, let's take out that 5 out of the equation and think about it in terms of, if you let my BOD bottle consume oxygen for 1 day and then check, you'll have some amount remaining. You'll have consumed some amount in 1 day, but you'll have some remaining, right? So the thing is, a 5-day BOD test does not degrade all of the organics in there. It's just a standardized time frame where we know that significant biological activity has happened. If we take a BOD bottle and let it sit there for 10 years and measure how much oxygen was demanded, we get a closer approximation of the total you could ever demand out of it, right? So when we say BOD, that the BOD remaining at time 0, this is like the ultimate amount, or essentially that's equal to BOD at infinity. So if you left it an infinite long amount of time, that's as much BOD, that's as much oxygen as the biological activity could possibly demand from that sample. Okay, so with that in mind, the L here is the amount remaining. So that means if we did a 5-day BOD test, we'd have some remaining. So what that would look like is down here, the L naught. So if we were to solve this in terms of LT, so L remaining at time 5 is going to be equal to the ultimate amount minus the amount that was demanded, the BOD, over 5 days. Okay? So that's kind of what I'm referring to, and the whole BOD concept is slightly backwards itself, right? Because we're measuring oxygen in place of something else. And this is then the amount remaining. Just try to keep in mind what's happening here. This is BOD remaining. That remaining is very important because BOD itself is the amount demanded. So the remaining amount that could be demanded is L. Okay, then we have, if we want to track it over time, referencing back to our mass balance a moment ago, if you're tracking this amount in a bottle with some volume, we would put the volume on both sides. That'll cancel. And the reason we do that, by the way, is really to have mass per time units. That gives us, when we work with mass balances, we're always dealing with how does the mass change over time, or maybe the number if it's like a number of bacteria or something. Okay, so this is essentially setting up a mass balance in our bottle, and then it derives, like I showed you a minute ago, to here with that same process. We can, based on that integration, we get LT equals L naught times e to the minus KT. K here is a constant that's describing the BOD reaction rate constant. It's a per time unit, which means, typically per days here. That means it's first order. Don't worry about that if that doesn't make sense. Okay, so all that in mind, coming back to the context of discharging water into a river, we need to be able to find this ultimate BOD, this L naught, based on the fact that we typically have a river and some sort of wastewater discharging into it. Okay, so we'll have a flow rate for the river, and the river probably has a little bit of BOD in it. Like I said, there's some biological material in it, rivers, and we're going to have the wastewater, we'll say L naught R, and the wastewater certainly has some BOD remaining. So we'll say L naught waste, for example. And so in order to find the actual L naught that we're looking for a problem, we'll see in a minute that some of our problems are going to say, okay, immediately downstream of a wastewater discharge. So the wastewater discharges into a river, we assume it mixes well, then what's our conditions? Because that's going to be our starting point to predict what's happening downstream. Make sense? Okay, so then this becomes I'm going to call it a mass balance again. This is so intuitive of a mass balance that you probably will recognize, oh, that makes sense. I didn't need to call it that mass balance, but that's just what I'm going to call it, okay? So here we have a Q for the mixture, and then L naught for the mixture is what we would be really referring to for our L naught here. And that's what this is saying is referring to, this is coming from the BOD in the river plus the BOD in the wastewater. Okay, so whatever amount could be demanded from those two are now going to be, that combination is going to be our ultimate, ultimate that we're starting with at this point. Okay, so that's going to be our starting point in terms of the amount of BOD remaining. Then we can have we can take that that term, that ultimate amount of BOD remaining, and say, well, we have some rate of deoxygenation that's related to that. We have the rate at which we're deoxygenating is directly related to that BOD remaining. So we have a term here, an equation, where we're essentially saying the rate of deoxygenation is related to a deoxygenation rate constant, which, by the way, it's pretty much the same thing as the K here. This K, there's a caveat I'll show you in a minute from the book I'm using, but it's essentially the same thing. So essentially, it's that rate at which the BOD is occurring, or that rate constant, it's how quickly is the BOD being removed, times that initial amount of remaining BOD times e to the minus KT. Okay, so that gives us a term that can describe the rate at which oxygen is being removed at a given time, given some starting conditions. Okay, we're going to contrast that particular rate with the rate of rearation, which is, I mentioned, a physical process. So the rearation is going to be a function of how quickly the river is moving, how turbulent it is, how shallow versus deep. And if you think about it, if you've ever had an aquarium, how do you aerate it? Well, it's either some sort of a bubbler, so an aerator, or you've got some water flowing maybe through a filter and then back onto the top of the water, and it's just providing some motion across the top of the water. Essentially what you're doing is increasing the surface area of contact between the air for oxygen and the water to re-aerate it. If you have a slow, stagnant, deep body of water, you're not going to get much oxygen through it, especially if it's hot. So if you think about southern Louisiana, and you look around and there's lots of ponds everywhere, And our soil here is rich with nutrients, all the sediment that's been deposited over the years. Basically, there's lots of biodegradable organic matter. So you add water, got lots of biological activity. However, we don't necessarily love that, especially if the oxygen gets depleted and then it starts stinking because there's the anaerobic processes, kind of start smelling maybe like wastewater or something. We don't want that, so you'll see fountains everywhere. The fountains in the ponds here largely are to aerate the pond, to keep it nice, keep it fresh. They're beautiful, but also they're keeping the pond aerated so you don't have some of these cases where you have too much deoxygenation occurring just based on the natural mechanics of or dynamics of those ecosystems. Okay, so reaeration then, in addition to those physical processes that are important, it also matters how much oxygen is missing compared to saturation. So if we talk about the amount of oxygen that we could have, the saturation, earlier we drew the dotted line and said, okay, well, we're usually kind of below that and might reach up towards that. Well, the difference between that saturation and some point along our curve, that's going to be our deficit. So the amount missing from the max is our oxygen deficit. We're going to call that D. If this is DO here, that line, and this is DO saturation. This is all spelled out a little clearly right here. So our deficit is just basically that gap. The bigger the gap, the more oxygen is being forced into it by the chemical equilibrium of that gas-liquid phase transitions, Henry's law type stuff. So if we have a bigger oxygen deficit, oxygen is being put into the water at a faster rate. Okay, so we can describe then that reaeration rate as Kr times the deficit D. So Kr times D, that gives us the, essentially if RD is that deoxygenation, that's the rate at which it's being removed, this is the rate at which it's being added. So at some point, in fact, that critical point, those two are going to be equal, right? The rate at which it's being removed versus added, once it stops moving anywhere, that's the moment they're equal. Okay, now Kr is defined as some function of the stream speed and the stream depth. This is pretty arbitrary. Well, not arbitrary, it's empirical. So researchers went out, studied like 100 different streams and rivers, and decided, well, if it's deeper, you have less aeration happening because, think of the Mississippi, it's over 500 feet deep in some places, or maybe a lot more than that. And think about the water towards the bottom. When's the last time it's been near the surface to see the air, to breathe a breath of fresh air? Chances are, statistically speaking, it's been a while. That means it's not getting much oxygen, at least if you look at the total volume in some portion of it. Not much of that is exposed to the air. The speed matters as well. So if you have a slow-moving bayou compared to a waterfall somewhere, you're going to get a feel for that difference in how much water is contacting with the atmosphere. Okay, so they studied a whole bunch and said, okay, well, they seem to relate in terms of the speed, 3.9 times the speed. If you take the speed to the 1/2 power, square root of the speed times 3.9 seems to be the number on top. And then on the bottom, we have the depth to the 1/2 power, or 3/2 power. So 1.5 power is what I meant to say. So it's related to the depth. The deeper it is, the less oxygen, the faster it is, the more oxygen. Okay, so it's just an empirical definition. I'll have that on the equation sheet. And that's giving us some way to calculate the rate constant here that's going to determine our system. That's basically a way to account for the physical features of a body of water. Okay, make sense so far? All right, and here's just an example of the reaeration rate constants. You can see that the range for a small pond backwater kind of system is going to be like 0.1 to 0.2 per day. And if you get up to a rapids or waterfall, you're up 1.15 or higher. So just kind of giving a frame of reference. Table in the book that I am teaching from. Okay, and I guess I missed the caveat. Don't worry about it. It's just KD is pretty much equal to the amount of BOD removal. That's the rate constants are essentially the same in many cases. Some cases they're different, but don't have to worry about it. Okay, so in terms of the modeling and looking at it from a kind of a schematic perspective, if you take a look at the oxygen sag curve, which we talked about, and then we also take a look at the rate of reaeration and the rate of deoxygenation. So this is, if you can't see, this is RD here for deoxygenation. And then here that's R of the reaeration, so probably spelling this wrong. Essentially, we're just taking a look at the rates for both of those. And what you'll notice is the rate of reaeration reaches a maximum at the same point where our deficit is the greatest, which makes sense. That's the critical point, and that's where we're solving the system. We also note that the rate of deoxygenation does intersect that exactly, because at that point, the two rates have become equal, so that the oxygen is at that moment is neither increasing or decreasing. So that's kind of the definition there. But of course, as more time goes on, biological activities consuming the food, and so the rate of deoxygenation is going to continue to decrease because the food is decreasing. So as soon as you cross that point, they're no longer equal, and the reaeration starts to outcompete it. If you think about, I'm an aquarium owner, and so if you ever start an aquarium and you are kind of dealing with the startup system, it's really important to have good aeration. If you had a bunch of fish and put them in a thing that did not have much air, it might take a few hours before there's enough BOD excreted by the fish or whatever. They could draw the oxygen down. Might take a little while. It's not instant. There's some dynamics as well with the nutrient cycling. End up accidentally producing a lot of ammonia. That would kill the fish. So there's other issues you could have. Maybe if you have a fish kill a week in, it's very likely that's ammonia has accumulated before the bacteria can convert it to nitrite then nitrate. Different story, but same process happening here. It's how quickly are these elements being transformed in that system, and at what time are you going to hit that critical point where it's the danger zone. Okay, so to model the deficit then, to figure out all this, we have an initial deficit, DO initial, and then a deficit at some time t. So we want to know what's the DD dt, so the change in deficit over time, to get ourselves an equation to deal with the system. So that's going to be essentially equating the deoxygenation. It feels backwards, right? We have oxygen deficit, so how much is missing. So the deoxygenation rate is increasing the deficit minus the reaeration, which is decreasing the deficit. So we do that, and then we could rewrite that as dd dt is equal to this kd L naught e to the minus kt minus kr times d. Okay, so your job is now to integrate that. But no one's laughing? Okay, good job. It was a joke, okay? I was hoping someone would just be like, just like smirk, like as if. I probably didn't give you enough time. Okay, just kidding. I don't want to bother with that. I don't want you to bother with that. Probably something you've learned in differential equations. I would imagine. Probably something I learned in differential equations, I bet, one day, a long time ago. But here's the solution when the book gives it to you, which is real nice. Okay, so it depends on the rate of deoxygenation, that initial BOD remaining, the rearation rate constant, the deoxygenation rate constant again, and all these things, and that initial deficit. So it is an integration of that equation. And there's kind of one caveat here that there are cases if these rate constants are equal to each other, if Kr is equal to Kd, we end up dividing by 0, which is not so nice. Okay, so there is an exception. So this is the equation. You'll see it on my formula sheet that I provide. One of the nice things about this modeling setup for the case of teaching you guys is you don't actually have to have the mass balance knowledge. This is kind of in line with, I think, how you've been taught this semester is like, here's the equation and maybe where it comes from and why it matters, components of it, and you apply that equation to the system rather than deriving to it. And we weren't going to integrate this one anyway, but avoiding that part of it, I think that works. So you'll have that, and then we have a second equation for the deficit here, but this one's only for the case where Kr is equal to Kd. Okay, so this one's provided as just in case these two happen to be the same, and these are the rate constants, not the rates. We talked about the rates meeting and being equal for a moment. Rate constants are different, right? This depends on the stream, depends on how quickly the bacteria are acting. Essentially, those are describing those two things. All right, so only use this one, only use the small one if Kr is equal to Kd. So only use that if you're dividing by 0 by accident, essentially, okay? All right, so that describes the deficit. So that means we have two different equations to find the amount of oxygen missing from the water at some given time, which is pretty handy. The last thing we need then is, okay, well, how do we know what time is that critical time? And we have one last equation here. We're just essentially, I think this was derived by saying at what point do the rates equal each other? So the rate of deoxygenation, set that equal to the rate of rearation and solve for T, because that's the critical point. I'm going to skip all the derivation here, give you the equation. This is the time, the critical time. We have the same problem of dividing by 0 potentially, and the book does not provide a solution to that, so we're just not gonna deal with that. If those happen to be equal, we're not going to solve a problem for time, or it'll be impossible, right? Okay. Maybe mathematically there's some other way. I'm not interested in that. I'm sure there's something to be done. Okay, so this will be another formula you have. This is essentially finding that time. It's based again on these parameters and the initial deficit, and that gives us a way to know at what point downstream do we have a potential problem. Okay, and then of course, if we have a stream or a river where we can assume that the velocity is constant, then we can say, well, the distance is equal to the velocity times time, or the time is equal to the distance divided by velocity. Okay, very, very simple stuff there. Just to expect you to know that. The units, by the way, are typically in here going to be kilometers and days. Of course, if you're given speed in meters, you could get distance in meters, but in terms of practical cases, it does take a few days before you hit that dissolved oxygen minimum, which means you've traveled, maybe 40, 50 miles, which would be kilometers in scale, right? So it'll be, you'd be kind of surprised to say, well, we discharge wastewater in Baton Rouge, but we got most of the way to New Orleans before we hit that minimum, right? That would be maybe a little bit surprising. And of course, it depends on all the dynamics of the river system. All right. Any questions on that? Yeah.
Can you go back like 2 slides?
This one?
No, the slide before that.
Yeah.
Between the A and A sub D.
Okay, so the K and the K sub D, like this one, essentially they're the same. That was the caveat I meant to mention. We'll just treat them all the same. There are, and I meant to add a slide here. I thought I did, and I didn't save or something. Because I taught this class earlier today. I had the same exact question. And it's like, shoot, I should know this, and I don't know. So the book actually provides a few sentences saying, most of the time these can be assumed to be the same, but it actually, because essentially the K itself is how quickly BOD is being removed. And then the KD is the de-aeration rate constant. So effectively, how quickly is oxygen being removed? It's the same for like slow-moving deep rivers, but when you have like a waterfall type situation, things change a little bit, and I think there's more availability for bacteria to interact with stuff. And, in our case, we'll call it the same. Yeah, I just need to update the slides. I thought I had. Yeah.
So K and KD are the same, and KR is the one that
KR is different. KR is the reaeration rate constant. That depends on the depth and the speed. Okay. So I've got a couple problems, and they're not starting, we're not starting all the way at the end of those equations. We're going to back up a little bit. This problem is going to deal with essentially finding that initial deficit. So we have a problem here. It says the wastewater from some other example has a dissolved oxygen concentration of 2 milligrams per liter and a discharge rate of 1.1 cubic meters per second. The river that is receiving the water has a dissolved oxygen equal to 8.3 milligrams per liter, a flow rate of 8.7 milligrams per liter, cubic meters per second, and a temperature of 20 degrees Celsius. Assuming complete and instantaneous mixing, estimate the initial dissolved oxygen deficit of the mixture of wastewater and river water just downstream of the discharge point. Okay, so we want, I always encourage you to draw your system first when you're going to approach a problem. So we have, the simple case would be just to draw river mixing instantaneously in this little circle, making a new stream that's combined. And you could draw it fancier if you want, but that's going to be our instantaneous mix spot. And then what we want to know is the dissolved oxygen deficit of the mixture just downstream of the discharge. So we're going to say this is going to be deficit equals question mark when we have some flow rate for the river and some DO for the river, flow rate for the waste, and DO for the waste. The book here is referencing some other problem, and it gives us a temperature. Essentially, we have different amounts of oxygen that can dissolve into water based on the temperature and based on chloride concentration and stuff. We're just going to assume that we're at 20 degrees Celsius, and we'll just say no chloride. So that's the DO saturation then, is the lookup table here, is 9.09 milligrams per liter, just coming from that table. Okay, so work with that for a couple minutes and see what you can come up with.
how did you know which concentration to use for?
I'm just assuming. maybe this other example problem has some value of chloride, and then you have to look up a different spot. But this was 20 degrees Celsius, and I just took that. I'm doing that part for you because I didn't want you to have to think about it. Okay, so hopefully you are able to kind of figure out the deficits for the two systems and start relating kind of, essentially we're doing a mass balance even if you didn't know it was called that. The total amount of deficit on either side has to be the same on both sides, but you have two different flow rates, right? So you have to combine those accordingly. So the way to do that would be to say what's coming into that little circle is the same as what's going out. You can say the QW dW is plus the QR dr is going to be equal to that Q for the mixture times the D for the mixture. And that D for the mixture is essentially going to be then our initial deficit that we're working with for the problem if we were to look downstream of that point. Okay, so then challenge then is to go ahead and solve for the deficits here, convert from the dissolved oxygen. Well, that's going to be 9.09 as the saturation value minus the two different values. So you get 0.79 milligrams per liter for the river and 7.09 milligrams per liter for the wastewater. And then, of course, the flow rate for the mixture is the two flow rates added. That's 9.8 cubic meters per second. So you can then solve this for the deficit of the mixture, and that's going to be equal to QR dr plus QW dW divided by the Q mixture. Go ahead and just write that 9.8 cubic meters per second. And you'll have cubic meters per second on the top and the bottom in each term. Those will cancel, and you'll be left with your deficit, which is milligrams per liter. Does that process make sense? Okay. So let me grab Excel. Okay, so I went ahead and put these values here. And so we'll say QR times QW plus dW times dr, all that divided by 9.8. Did I do some? Okay, and that comes out to be about 1.5 milligrams per liter. I feel like I had a slightly different number this morning, so if you see something that I did wrong or entered wrong, it was like 1.5 in both cases. But one time it was 1.49 this morning, and now I'm like 1.54. Did I do something? Do you see anything? Okay. Well, I think maybe I punched in a number wrong this morning or just now, but essentially that process is the same. The answer, fortunately, is the same. So if I did something wrong, it was small and it might not have been today, or this class. Okay. That makes sense, though. You guys are seeing the two rivers coming together. That's a mass balance. There's no reaction involved, but that's a mass balance. Okay. All right, so we don't have enough time for this problem to go through it together, but let me just talk you through it, and then I'll show you some solutions I have for this problem from another time, and I'll post the solutions so you'll have that as a reference since you don't have this this textbook. So this one is saying just below the point where a continuous discharge of pollution mixes with a river, the BOD is 10.9 milligrams per liter. The DO is 7.6 milligrams per liter, and the waste mixture has a temperature of 20 degrees Celsius. The deoxygenation rate constant, KD, of 0.2 per day, an average flow speed of 0.3 meters per second, average depth 3 meters, and it's just some continuation from another problem. Okay, so this problem is asking us to find the distance downstream at which the oxygen deficit is at a minimum, and then also find that minimum value of dissolved oxygen. Okay, so I have, go to it. I have some notes from, it was, I think this past spring, or maybe even the one before. I solved this problem for a class, and essentially, I've got the solutions written out here. So I will post this. I think it includes the solutions to the one just a moment ago. So yeah, you'll have both of those. Take a look on your own time. Might be helpful with the homework as well. Any questions? Issues? All right, so on Thursday we'll go through your homework and any questions you have for the exam.